Can you see the screen? Yes, Khalid, can you see the screen? Hello? Yeah, okay, fine. So what is the coordination number of body center atom in the BCC unit cell? Yeah, correct. That is 8. Each point in crystal lattice represent an atom. These points are called lattice points or lattice site. Very good, correct. Now we have got, okay. So this is OBR, that is ortho. In the ortho position, there is bromine group. And then we have C6H4, that is benzene, obviously. Then we have CHCH3. Minus here. Assalamu alaikum, Salman. How are you?
Welcome, sir.
How are you? Good.
Alhamdulillah. Yes, sir.
How is Ramadan going on?
Alhamdulillah, sir. It's going good.
It's going good. Okay. Did you do the assignment?
Yeah, I did this assignment and I have sent it also.
Yeah, I also sent it. Okay. Nice. Yeah. Okay, so here we have, okay, this is not right, by the way. Khalid, the structure is not right. So I was wondering about the structure only. If the structure is not right, the structure would be something like this. Although your name is fine, I don't know how. You have written rightly, this will be Br, but here you will have a CH group. Here you will have a CH group, which will have CH2, CH3, and there will be a CH3 group like this. Okay, so this is the molecule. Now it is correctly written, it is 1 bromo, and then in the second, then what do we have? This is the first position, this is the second position. In the second position, we have a propyl group, which has a methyl group attached to it. Okay, so in the second position, we have one methyl propyl benzene, one methyl propyl benzene. Okay, so the name is correct, but the structure is not right. Okay, the structure is not right. Okay. Assalamu alaikum, Maimuna, how are you?
Walaikum salam,
Fine. How is Ramzan going on? Ramzan Mubarak, first of all. It's going good?
Yeah, same to you.
Okay, thank you. Yeah, coordination number is 8, the depiction of 3D arrangement of constant particles of crystal lattice. Oh, this was the question about crystal lattice. Okay. I actually asked, what do you understand by lattice sites? So each point in crystal lattice represents these points are okay, fine. You have also answered that. 1 bromo. In the second question, we have 1 methyl propyl benzene. That is correct. Okay. Now moving on to Salman's. Yeah.
Sir, sir, did you try this one, spline tool?
Yeah, I did try. But it will take, I mean, it took me a bit of time. I found some other websites and which are specifically for solid state chemistry. Okay.
Then that would do.
That was better for me. 1 bromo, 2 methyl, 1 methyl propyl benzene. Okay, correct. So all these are fine. Now, Mazia is also here. How are you, Mazia? Hello, Mazia. How are you?
So I'm fine.
Okay, so where is your assignment? Hello, could not hear you. There's a lot of noise. Did not do?
No.
Why? Why, Mazia? What happened?
So school stuff.
School stuff? What school stuff? अभी तो start ही हुआ होगा school ना, तो stuff होने लगा school में.
No, our school started already.
Yeah,
1 week.
One?
1 week is over.
1 week is only over ना, तो अभी वही तो बोल रहे हैं, like अभी start हुआ हुआ है school, and what stuff are they giving you guys, huh?
No notes and all. But I will do
No,
it.
हाँ, you have to do, okay, you have to do 3, बस 3 सवाल थे उसमें, है ना, उसमें आधा घंटा क्या 15 मिनट भी नहीं लगता, वो भी बिल्कुल ऐसे सवाल जो आपने क्लास में किया था, ओके, प्लीज डू इट, ओके माजिया,
Okay.
या, ओके, हाउ आर यू आयशा, अस्सलाम वालेकुम, आयशा, am I audible? Okay, so where is your assignment? आपने assignment नहीं दिया? Miss Aisha, what happened?
So last class I couldn't attend, so I'll submit today.
Okay, but did you watch the recording then? Yes, Aisha.
Sir, I saw it on YouTube.
Okay, you saw it on YouTube, na? Okay, fine. Good. Okay, so in the last lecture, so we were talking about, so we were mainly talking about the body-centered cubic, and in that we saw the Z for BCC atom, the relationship between A and R, and then the coordination number, and after that the packing efficiency, and after that we defined crystal lattice. Okay. Now we will be moving on. Okay, I have a question for you guys. So we had 1D packing, and then we went to 2D packing. So in 2D packing, we had 2 different arrangements. There was square closed packing, and there was hexagonal closed packing, right? And from square closed packing, we went into 2 arrangement, and we found simple cubic, and we also found BCC. Now between in the 2D solids, we had square closed packing in 2D and hexagonal closed packing in 2D. When I compared these two, then I found out that HCP is a better solid, right? Yes or no? Because it has more packing efficiency. Okay, Lamia is also here. How are you, Lamia?
Fine, sir.
Fine. Okay. Did you submit the assignment? आपने किया था? No. आपने
No,
नहीं
sir.
किया. अच्छा. Okay. Did you watch the lectures, the previous lectures, Lamia?
Yes, sir.
Okay. Any doubt in that?
No, sir.
No. Okay, fine. You are making notes. Everyone is making notes, right?
Yeah, I make.
Okay, fine. Great. So now look at your notes and tell me which is a better solid, HCP or SCP? The AAA type in 2D or ABAB type? Which is better?
Sir?
Yes, Lamia. Yes, Lamia, hello.
Yes, sir.
You were asking something. You said, sir. मैमूना, it is HCP. आपका C बटन खराब है क्या कंप्यूटर का, लैपटॉप का, फोन का? मैमूना?
Yes, sir. Sorry,
नहीं, बाय मिस्टेक आप लास्ट क्लास यही कर रहे हैं, क्या हो गया? दिमाग में आपके HCP छप गया. First time hexagonal close packing. Okay, so this is close. Close means they are near. Okay, fine. HCP is a better solid. Okay. If I compare simple cubic and body centered cubic, then which is better? If I compare simple cubic and BCC, which is better solid? Look at the packing efficiency and then answer. Yes, Salman, correct. I'm looking for more answers. Mazia, Maimuna, Khalid, Aisha. Which is better solid, simple cubic or BCC? Compare the packing efficiency and tell me which is a better student, which is the better solid, same type of question. You have to look at the marks. And the marks in the case of solid state is the packing efficiency. You can send the answers in chat now. Yes, Mazia, Khalid, Aisha, Lamia, Maimuna. What happened? एक ही आंसर दिया बस आप लोगों ने. Which is a better solid? Simple cubic or BCC? Okay, I have got answer from Khalid now. Yes, Aisha. Which is the better solid? Simple cubic or BCC? Aisha, what is Aisha? Can you hear me? आप लोग ऐसे शांत मत बैठा कीजिए ना please. Aisha, can you hear me?
Yes, sir.
What is the packing efficiency? You understand my question? Yes or no? First of all, tell me that. Which is the better solid? Do you understand my question, Aisha?
Yes, sir.
Okay, fine. You have answered it. Okay, fine. Okay, Maimuna. Okay. हाँ guys, start revising. माजिया तो अभी भी HCP नहीं है. हम तो यहाँ पूछ रहे हैं. I'm asking about simple cubic and BCC. Which is better, Mazia? Look at your notes and compare the packing efficiency. Na? I'm telling each and every point. Why are you still answering HCP? Which is better, simple cubic or BCC? Mazia. Okay, Mazia, can you please turn the mic on? Hello. Mazia, can you please turn the mic on? Yes, tell me, what is the packing efficiency of simple cubic? Look at your notes and tell me. I can't hear you. What is the packing efficiency of simple cubic? नहीं तो फिर you have to watch the lecture ना माजिया. ऐसे कैसे चलेगा? आप स्टार्टिंग में ही जब इतना नेग्लिजेंट रहेंगे तो फिर आगे क्या होगा? Okay, please watch the lecture at least then if you have not attended the class ना. अब आगे आपको क्या समझ में आएगा नहीं समझ में आएगा, प्लीज स्टार्ट अटेंडिंग द क्लास रेगुलरली. Now those who have answered it correctly, BCC, that is body centered cubic, has a greater packing efficiency than simple cubic, and in the case of 2D structure we saw that HCP has a better packing than SCP. Now in both the cases one thing is very common. In HCP also we put atoms under depression, and to make BCC structure we had put atoms on void. Is that correct? Yes or no? In ABAB we put in depression, and in BCC we put atoms on void. And in both the cases where the packing efficiency is low, that is square close packing and simple cubic, in both of these cases we put atoms on atoms. Right? All of you understand this whole phenomena that we have seen, the one observation, that if I put atoms on atoms, I'm getting a bad packing. Yes or no? Yes or no, Khalid, Lamia, Maimuna, can I get yes sir, no sir at least?
Yes, sir.
Yes, sir.
What is happening, guys? रोजा लग रहा है क्या आप लोगों को? हाँ? Okay, so that means if I put atoms on atom, that means it will give me a bad packing. It will give me a bad packing efficiency. And if I put atoms on voids, then it is going to give me a better packing efficiency. So when I am going to make a 3D packing from HCP, so we made 3D from SCP also and got simple cubic and BCC. Now we will keep the base as HCP and then make a 3D arrangement. So when I am going to make a 3D arrangement from HCP, I will not be putting atoms on atoms, because I know if I put atoms on atoms, then I will be getting a bad packing efficiency. I will be getting a bad solid. So I will start putting atoms on the voids. Now from here, please listen very carefully. Don't write anything. So first of all, let me make the BCC packing. Sorry, let me make the HCP packing in 2D. But make sure that whatever circle I am making, these are not circle, rather these are spheres. Okay, these are spheres. Okay, I hope this is a, yeah. Yes. So we have got our HCP, right? But please remember that these are all footballs, these are all spheres, and these are not circles. Now, there is the first observation that I want all of you to look at. There's the first observation. The first observation that I want all of you to look at is the voids. What is the void here? They are all triangular void, right? Yes or no? All of them are triangular void,
Yes.
right? But there are two types of triangular void. You can see that there is a triangular void in which the triangle is headed upwards, and there is another type of triangular void in which the triangle is headed downward. Yes or no? Can all of you see
Yes,
this?
sir.
Okay, very good. Now what I will do, I will first of all take an atom and I will start putting it on the layer. Now I can do only one thing. What I can do, I can keep atoms on the void. I will start keeping atoms on the void, and let us see that I'm starting to keep atoms on the triangular void, which is upward. So I will take a different type of atom and I will place it here. Now, as soon as I have placed this atom on the void that is made by 3 atoms, I have this particular void that was triangular in nature initially. Now it has become a tetrahedral void. Is that clear? Yes or no? Yes or no?
Yes.
Right. This was when the black atom was not there, it was a triangular void. As soon as I kept the black atom, it became a tetrahedral void. Is this clear? Yes or no? Please tell me.
Yes.
All of you.
Yes, sir.
Yes. Now let me put another atom. Don't write anything. Now again, the second triangular void that was in upward direction, it has become a tetrahedral void. Now it has also become a tetrahedral void. Now let me put another atom. Now I will put an atom on this particular void. Okay, so this is upward and I am putting it here. So again, all of these triangular void, they are now tetrahedral voids. Yes or no? Yes or no?
Yes, sir.
All of you can see this. Yes or no? Maimuna, Khalid,
Yes, sir.
Mazia, Salman.
Yes, sir.
Very good.
Yes, sir.
Now listen very carefully. Now listen very carefully. Okay. Look at the 3 red atoms that I am marking. Look at these 3 red atoms. This red atom, this red atom, and this red atom. Okay. Look at very carefully. And now look at the black atoms that I am marking. This black atom, this black atom, and this black atom. Do you observe something? That the downward facing triangular void, which is this one here, it has become an octahedral void now. Yes or no? Do you remember? You remember, right? I have told you, if you have one layer in which it is, the atoms are they're arranged in a way that they are making a triangle which is downward, and there is a upward triangle made, then this is also an octahedral void arrangement. Yes or no? You guys remember it? Yes or no?
Yes, sir.
है ना? So यहाँ से आप देखिए. Now what I will do, I will just go back a bit and let me just erase these black parts also. Okay, this is going to be a bit tricky. इसको रहने देते हैं. So here we have this yellow one. This yellow void is an octahedral void. Okay, I hope all of you can see that, right? Yes, yes or no? First of all, tell me that. If
Yes,
you
sir.
want another
Yes.
explanation, yes, no, okay, no problem. See, these are the things that people don't understand in solid state chemistry. Okay, so what we had done, we initially had 1D, then we went to 2D, and in 2D we had 2 different arrangements, right? In 2D we had 2 different arrangements. We had one arrangement which was HCP, and then we had one arrangement which was SCP, hexagonal and square plane and square close pack. And after that, when we went from HCP to 3D, when we were going from HCP to 3D, in HCP we found out that there are 2 types of triangular voids. Okay, we found out that there are 2 types of triangular void. Triangular voids. Okay, no, wait a second, let me name it properly. Don't write anything. Triangular void. Now there are two types of triangular void in HCP. There are triangular void which are upward facing like this, and there are triangular void which are downward facing like this. Now, when I start to put atoms on this triangular void, that is upward facing triangular void, then what happened? Then we got a, what did we get? We got a triangular void. These triangular void, they converted into tetrahedral void. Okay, so TD is short form for tetrahedral. And these downward facing triangular void, it became and got converted into octahedral voids. Is it clear till here? Yes or no? Please tell me. You understand this flow chart?
Yes, sir.
Right? Okay. Move it a bit here, and also I need to make this a bit small. Okay, now there is one more thing that I have to tell you guys. There is one more thing I have to tell you guys. Now, this triangular void that I have marked as black, this one, this tetrahedral void now, it is made up of 4 atoms, right? This one, it is made by 4 atoms, correct? Yes or no?
Yes, sir.
Yes. And in this particular void, let me make a few more atoms, then only I will be able to show you guys. Wait a second. Rather, what I will do now, I will label this one as red void. Okay, this is red void. Now, this red void has been converted into tetrahedral void. And then we have a yellow void, which is now octahedral void. Okay, this is now octahedral void. Now, I want your focus into a new void. Okay, into a new void. Look at this void here, which is made up by these triangles. Okay, this void. Can you see this void? All of you? Yes or no? This is a new void, right? And this new void is made by 4 atoms. And these 4 atoms are what? These 4 atoms are the 3 black atoms and the downward red atom. Yes or no? So it is a tetrahedral void, but in the opposite direction. You have
Yes, sir.
3 black and then 1 in the red atom. Okay, like this. So this is a new type of void that you have seen. It's a new type of void. So we have a new tetrahedral void. So as soon as I put atoms on the upward facing triangular void of HCP, I have converted the upward facing to tetrahedral void. I've converted the downward facing to octahedral void, and I have also got a new type of tetrahedral void. I've also got a new type of tetrahedral void, which is made by the new layer. We have made a new tetrahedral void. Let me write it TV. Okay, and this is I am marking as black. Okay, this is I am marking as black. Okay, and this is made by layer A. I will call this layer A because this tetrahedral void, it has 4 atoms. 3 of those atoms are red atoms, and that is the first layer. The second tetrahedral void, it is made by 4 atoms, 3 of which are black. That is, and it is the second layer. That is why it is the B layer. Okay, so we have got tetrahedral void of layer A and layer B, and we have also got octahedral voids. Now, all of you can see all these voids very clearly. Yes or no? Please tell me.
Yes, sir.
Yes. Okay. Very good. Very good. Now we have got a new types of voids. There are 3 voids now: tetrahedral void of layer B, tetrahedral void of layer A, and octahedral voids. Now I will again start and I will put atoms. Okay, I will put atoms. Make this black. Yeah. So now I will put a new type of atom. Okay. Now, if you focus here, you will see that if I put atom on this void, first of all, let me put the atom. Get this here. Okay, and let me put atom on this void. Okay, because I don't want to put atom on atom. What I want to put is I want to put atoms on the voids, atoms on the void. But if I try to put atoms on the tetrahedral void made by the layer A, that is the first layer. If I try, let me try that. Okay, let me try that. What will happen? So the tetrahedral void of layer A is marked by red. So this is the void. But if I put the atom on top of it, then I am not putting on top of the void. Rather, I am putting on top of an atom. That is why this arrangement will not be useful. Right? So even though it seems like I'm putting atom on the void, but essentially in reality, what is happening? In reality, I'm putting atom on atom. Yes or no? If I try to put it here, see, if the yellow atom is put on top of the tetrahedral void, so in practical and in reality, it is rather putting an atom on atom. Yes or no? All of you can see that? Yes or no?
Yes, sir.
Yes. Okay. Fine.
Yes, sir.
Now what I will show you guys. Now what we will do? We will put this new layer. Let us say on the octahedral void. Okay. So we'll put this on the yellow void. We will put the new layer on yellow void. So when I take this atom and I put it here, this is very good because this is very fine because what is happening? Because I am putting atom on void and I am not putting atom on atom. Correct? Yes or no? दिख रहा है आप लोगों को yellow वाला? All of you can see this yellow, right? Okay. Similarly, what I will do, I will put it in the next atom, next void. So you can also see now I am putting it on the octahedral void, right? This is the octahedral void. I'm marking them here. These are the octahedral voids that I am focusing on. And I will be putting atoms on those voids. So jab tak ye ban raha hai, till the time I am making this, you can understand it. But after I am done making it, you will not be able to understand. Okay, so please keep your focus here. Now, so now we have got an arrangement. And as you can see, if I put atom on the octahedral void, then what is happening here? What is happening? I have got the first layer that is red. Okay. Then I have got the second layer that is black. Then I have got the third layer that is yellow. Correct? Yes or no? Yes or no, guys? Tell me. Right? Okay. Now, again, let me just take this. And I want to show you guys here. Bringing it big. Okay. Now, it may seem very clumsy, but let us keep our focus. Okay. Let us keep our focus. Now, we were putting atoms on these voids, right? These voids, right? These are the yellow voids in which we were putting the atoms, correct? Now, as you can see, I have made these atoms here and I have put it here. Okay. And then we have the black atoms like this. These three black atoms. Can you see?
Yes, sir.
Yes or no? Okay. Now, these yellow and the black, they are making all of you once again. Okay. Once again, let us focus. The yellow ones is here. Then we have the black one here. Okay. Let me also darken. Okay. Let me just get. So these are the black one. Okay. And what are the yellow ones? These are the yellow ones. Okay. These three. Now they are giving up a new octahedral void. These are giving up a new octahedral void, right? And this new octahedral void is here. This part. This is the new octahedral void. Okay. So let me just get this red here. And you can see this is the octahedral void that I'm talking about. Okay. The black triangle and the yellow triangle. And if I want to put atom on that, you will see that I am rather putting atom just in the place of the red atoms, right? So again, from red, black, I have got to yellow, and after yellow, I have got again red atoms. Yes or no? See, I'm putting it on the octahedral void made by yellow and black atoms. So I am in the same way putting atoms in the red arrangement. Yes or no? Can all of you see this?
Yes, sir.
Right. Okay. So let me take it away. So what I wanted to say is that we had red atoms, red layer, 3 atoms from the red layer, 3 atoms from the black layer. They made an octahedral void on which we put the C atoms, right? On which we had put the C atoms. Now what happened? Now we got a new type of octahedral void made by black atoms and the yellow atoms. And if I put atoms on that void, on that octahedral void, I will again get A atoms. Then again the sequence will carry on. You will have C atoms and A atoms making an octahedral void. And then again, if you put atoms here, you will get the B atom, B layer. Okay. So this is the arrangement that you will get. You will get A and B making an octahedral void and put C atoms, B and C making octahedral void. Then again, you will have A atoms. So ABC type of arrangement you will get if I put atoms on the octahedral void. Is it clear? Yes or no? Please tell me. ABC type?
Yes, sir.
Yes. Okay. Now, let me take this bit down. Okay. Now, we have also seen that tetrahedral void A, if I put atoms there, it is not very useful. Now, let us try and put atoms on tetrahedral void of layer B, tetrahedral void of layer B. So, tetrahedral void of layer B, let me take this and bring it here. Okay. So, tetrahedral void of layer B, which are those voids? So, those voids are, okay, I have to remove this yellow atoms now, first of all, then only I will be able to make it. So let me copy and, okay, actually I got disconnected. Okay, now I want to put atoms on the tetrahedral void made by layer B. That means these voids, right? This black one here, this black one here. Okay, so these are the voids in which I have to put the atoms, So let me take an atom and I will show you that if I put atoms on this void, the black one, so which layer it is? If I'm putting atoms here on the black void, it is again the layer A, right? Yes or no?
Yes. Yes, sir.
Right, all of you can see. So these are the black ones. If I put atoms on top of the void, I am again getting the layer A. I am again getting the layer A. So this is essentially AB type. Essentially AB type. Okay. So here you have got AB type. This is, if I put atoms, let me put atoms only. Okay, so this is your AB type. This is ABC type. Okay. So all of you, please write this chart. Main thing is chart. These diagrams can be again made if you understand the chart. Okay. So this 1D, then 2D, and in 2D you have SCP and HCP, and then from HCP what I am doing, I am moving towards 3D. So please write this down. Yeah. Raise your hand if you're done, okay? Also, you can write a note at last for both the packing, okay? For both packing. For both packing, number of tetrahedral void is double the number of octahedral void, okay? Because you can see you have one octahedral void and there are tetrahedral voids from 2 layers, okay? Both in ABAB type and ABBC type, tetrahedral voids will be double the number of octahedral voids. If all is done, please raise your hand if you're done, okay? Lamia is also done. Okay, fine. Just waiting for Mazia now. Okay. So first of all, let us start with ABC type, okay? ABC type in 3D. Okay. So in this, I have to take a set of atoms. Okay, I have to take a set of atoms and make a unit cell out of it. Okay, this is the first problem that we have. We have to make a unit cell out of this arrangement. Okay, so first of all, I have to choose a set of atoms. I will be choosing a set of atoms. Now, what I will do, I will start with a red atom. I will start with a red atom. So let me choose one red atom very carefully. Now, I want all of your focus on this red atom. All of you can see this red atom, yes or no?
Yes, sir.
Okay, so that is the first atom that I am going to take. Okay, that is the first atom that I'm going to take. Okay, in the second layer, for the B layer, that is the black one. Okay, that's the black one. What I will do, I will take a set of atoms. I will take a set of atoms. So this is here. Let me mark which of the atoms will I take. I will take these atoms here. This atom, this atom, this atom, this atom, this atom, and there is one more atom that will be here. This adds into these atoms. Okay, so these are the atoms that I am taking for the black one for the second layer. Okay, so I've got how many? 1, 2, 3, 4, 5, 6 atoms I am taking for the black one. Okay, I need to make it a bit small. Please just listen, don't write anything. Similarly, I will take the yellow atoms, and the yellow atoms are these ones. 1, 2, 3, and there will be 3 more like this. Okay, as I have taken the black one, but they will be just in the opposite direction. So let me just copy, paste this, make it yellow, and then rotate it vertically, right? Okay, so these are the atoms that I have taken. I think I need to decrease the size even more. Okay. Now, again, the next layer will be obviously the A layer, that is the red atoms. So let me place it here. Okay. So I have taken a bit of atoms, and now I will be taking their points. I will be taking their points and making a unit cell out of it. Okay. So these are the atoms that I'm interested in. I will be making unit cell out of these atoms that I have taken. As you know, we can take whatever atoms we want. We can take whatever arrangement that we want from the packing to make a unit cell. So let me start. Let me draw the red one here first of all. So this is the red one. Okay. I think I might need a more space. So let me write it here. Then we have the 3 yellow ones. Then we have the 3 yellow ones, right? Then we have the 3 yellow ones. Oh, wait a second. I think these will be like this. Wait a second. Sorry. They will be in opposite direction, but they will be facing this manner. Yeah. So then we have a 1 yellow atom. So just beneath this red atom, I have a yellow atom. Just below the red one, I have a yellow one. Then I have 2 other yellow one here and here. So I'm taking a midpoint. So you can imagine I'm taking a midpoint here. Then I have 3 yellow one next to it. Then this yellow is just beneath this yellow. And then I will have a yellow here. Okay, then I have the black one as it is. I have the black one as it is. Let me make the yellow once more. So what I will do, I will just take these points and make it black and then flip them vertical. So these are the black atoms. Right, guys? Same manner, we have one black atom, then two black atoms, then three black atom, and after that we have a red atom here. We have a red atom here. Now I will join these points. I will join the points. So when I join the points, I hope it should not betray me. Okay, so let me take it black only. You may be wondering what type of shape we will be getting, but please have some patience. We will be getting good atoms, good arrangement only. A shape that you have seen many times. Can all of you see a cube? Tell me.
Yes, sir. You can see the cube.
And then you can see the atoms, they are present in the corners and also in the face centers, right?
Yes, sir.
Right, they are present in the corners and in the face center. So you can see that all this complex looking arrangement, we can take a few atoms and we can take a arrangement of few atoms and then produce a very beautiful looking, very clear looking unit cell, that is the face centered cubic. Okay, this unit cell is what? This unit cell is known as face center cubic. And this packing, it is ABC packing, but it has also one more name, which is known as cubic close packing. Cubic close packing. So when you have this arrangement that is CCP, okay, so the unit cell of CCP is FCC. Okay, this is also one more point that you have to remember very carefully, because they may use FCC CCP alternatively, interchangeably. So you must remember that the unit cell of CCP, that is cubic close packing, is FCC, face centered cubic. Okay, so now please draw these atoms and then the FCC unit cell. Okay, the FCC unit cell. Then we have to look at its Z, the coordination number. Then we also have to look at the relationship between A and R, and then the packing efficiency. Okay, but those things we have already done many times. The arrangement was the major picture that I have to show you guys. The rest of the other things that can be easily understood. Chali. Please start writing, then raise your hand if when you are done. By that time, I am retouching this whole thing. We have a yellow atom here. So these are the yellow atom corners. Then we have the black atoms here and here. We have the red atoms here and here. Black atom is here also. layer A. This is the layer B. This is the layer C. So again, a layer A. One more thing that is very important about a unit cell is that you have to end with the same layer that you started with. So if you started with A layer, then you have to go till A layer and then stop it. You will see this pattern everywhere. If you look at our square close packing, then also, and if you look at our hexagonal close packing, then also you can see that I started with A, then B, and then again A. Simple cubic is simple because it is just one layer. Then here ABC, ABC, in that I have to take a unit cell in such a way that the first layer is A, then B, then C, then again A. You have to complete the cycle. Please raise your hand if you're done. Okay, many are done, I think. You're just waiting for Khalid. Khalid, raise your hand if you're done, okay? Okay. So let us first of all talk about the coordination number in this type of packing. Okay, let's talk about the coordination number in this type of packing. Coordination number. Okay, coordination number. So for that, what I will do, I will show the coordination number in two ways. I will look at the packing. Okay, so this is the packing, right? I will show you the coordination number in this packing. Then I will show you from the unit cell also. Okay, so let us concentrate on this packing right now. All of you can see this packing, yes or no? अरे हाँ ना तो बोलिए. Now tell me, can you see this black atom? You can see this black
Yes.
atom, yes or no? Okay. Now this black atom is surrounded by 6 black atoms on the same layer, right? 1, 2, 3, 4, 5, and 6. So it is touching the 6 black atoms on the same layer, correct? Yes or no?
Yes, sir.
And then we have these yellow atoms on top of the black atom, right? These 3 yellow atoms. These are also what? These are also touching the black atom, yes or no? and that is why it is making a new tetrahedral void, right? With this black atom, and you can see that there are three yellow atoms, and then we have the black atom. So those yellow atoms are also touching the black atoms, and then only they are making a tetrahedral void. Please remember, you can make tetrahedral void if you have black atom here, and then you have three yellow atoms like this, right? So you're making a tetrahedral void. Okay, so all these yellow atoms must be touching the black atom. Okay, all of you can see these three yellow atoms, yes or no? Yes or no, guys? Nahi dikh raha?
Yes, sir, we can.
Okay, now I want your focus, not because it is getting clumsy, I want your focus on the red atoms that is present. So this was our black atom. I want to again your focus here. Let me highlight it in some way. Okay, so this is the black atom that we are focusing on. Okay, and then we have this red atom. We have these three red atoms in the A layer, on top of which the black atom was put. Yes or no? This is the layer 1, then black is the layer 2, right? So the black is touching 3 red atoms. Then in the second layer, the black is touching 6 black atoms. Then the black atom is touching the 6 yellow atoms. Can all of you see that? Yes or no? Please tell me. This is the black atom here. This.
Yes, sir.
What about others? Maimuna, Mazia, Aisha. This is the black atom. It is touched by these yellow atoms. And it is also touched by these red atoms. Okay. So we have 6 on the same layer. Black is touching 6 black, 3 yellow, 9, 3 red, 12. So the coordination number is how much? The coordination number is 12. Okay. Now what you can see? You can also see the coordination number if you want from this unit cell. From this unit cell. How will you see? So first of all, if you take one black atom, take any black atom. Let us say this black atom. Okay, so this black atom, it is touching which atoms? What atoms it is touching? Tell me. If you look, this distance is A, and the distance between these two black atoms is √2 A by 2. Correct? Yes or no? No, ये नहीं आ रहा किसी को. Okay, let me show you guys. Let me first of all make a face-centered cubic like this, in this manner. So here we have a black atom. Okay, here we have a black atom, and then in the downward we have a red atom here. Okay, so this distance is how much? This distance is A, but we have black atoms in this face center. Here we have a black atom, here we have a black atom. The distance between these two black atoms is obviously less than this A, right? Because it will be A √2 by 2, because this whole phase diagonal, it is going to be A √2. And in the midpoint, we have an atom. That is why this will be A √2 by 2. Yes or no, guys? Tell me. Are aa raha hai ki nahi aa raha hai? Can all of you see this? What happened?
Yes, sir.
Yes, na? Now this 2 is near. So this is touching 3 of these black atoms, right? It is touching 3 of these black atoms. Similarly, it is touching 3 of these black atoms. Now, this black atom will also be touching which other atoms? So in this floor, it will be touching these. Wait a second. So this black atom is present in 8 rooms, right? It is present in 8 rooms. This wall is present in 2 rooms. That means this black atom will be touching How many walls? It will be touching only 4 walls, essentially, because it is present in 8 rooms, but the walls are present in 2 rooms. The walls are present in 2 rooms. That means there will be 4 rooms common. There will be 4 rooms common. And in each cube, it is touching 3 atoms, right? 1, 2, and 3. Similarly, it will be touching 3 atoms in all the 4 individual rooms in the individual rooms. 4 threes are 12. So if you look even from this corner one atom, you can say that it is equal to 12. Now I have 2 tasks for you guys. The second one is after coordination number, the Z. Okay. So in the Z, what you can say? Z, you can say that there are corner atoms. And there is face center atom. So corner atom are how many? There are 8 corner atoms, and there are how many face center atoms? 6. What is the contribution of corner atom? It is 1/8. What is the contribution of face center atom? It is 1/2. So for the corner atom, you have 1 plus, you will get 3, and hence the Z will be equal to 3 plus 1. Yes or no?
Yes, sir.
Right. Face center will have half contribution, and there are 6 faces. Corner atom has 1/8, it has 8. And then Z will be equal to 3 plus 1. Okay. Fine. So you copy from here. Okay. You copy from here that the coordination number is this much, and the face center contribution is this much. And then you have to find relation between A and R. And please remember, these are the atoms that are touching each other. Okay. These are the atoms that are touching each other. And hence you have to find the relationship between A and R using these 3 atoms that is present in the corner, face center, and then again corner. Okay. So you have like 15 minutes. I will go have my iftar, pray Maghrib, and then come back in 15 minutes. Okay. Fine. I will be back in 15 minutes. You have this work to calculate the relationship between A and R. I have told you what atoms are touching. Please refer back to the BCC type and simple cubic type of structures, and then see how I have taught you guys to calculate the relationship between A and R. Okay, chalo. Thank you. I will be back in 15 minutes. So anyone was able to find out the relationship between A and R?
Trying, sir.
Trying, still trying. Okay. So let me help you guys. So I've represented these atoms, the corner one, the face center, and again the corner one in this manner. Okay. Now, those who have attended the first class, they may remember that the phase diagonal has a length of a root 2. Yes or no? This length is a root 2, right? Khalid, Maimuna,
Yes, sir.
Salman, right? And then this is R, this is 2R, and this is again R, correct? Yes or no?
Yes, sir.
Now you guys tell me. We have 4R is equal to a root 2, correct?
Yes.
अब बताइए यहाँ पे we have 4R is equal to a root 2. This is our relationship between A and R. Okay, so the important thing is that you have to look at the atoms that are touching each other. Atoms that are touching each other. So we have got Z, we have also got the relationship between A and R. Then we are going to find out the packing efficiency. Packing efficiency. Okay. So packing efficiency, this will be equal to the Z into, right? Z into the area or volume occupied by here, because it is sphere. Volume occupied by one atom, that is 4/3 pi r cube divided by a cube into 100. So what is the value of Z? 4 into 4/3 pi r cube divided by a cube. Instead of a cube, what will you write? A is equal to 4r upon root 2. Right? A is equal to 4r upon root 2. So please solve this packing efficiency. I hope you guys are calculating, okay? Here we have 4 into 4 into pi r cube divided by, this will be 4 into 4 into 4 into r cube, and this will be into root 2's cube will be 2 into root 2 into 100. So I can eliminate 4 and 4, r cube and r cube. Then I can eliminate this 2 and this 4 by 2, and then again this root 2 by this 2 be root 2. So I will get pi divided by root 2 into 100. Yes, I think you have done it correctly. There is some slight calculation mistake, not calculation mistake, but the mistake due to approximation of the values of root 2 and pi. So actually, if you solve this, did I leave something else here? Wait a second, this is not right. कुछ तो यहाँ पे गड़बड़ी हुई है मेरे से.
Sir, it will be
Yeah, into 3 is
4
remaining.
upon, yeah.
Into 3 is remaining, right. Here we have then pi upon 3 into root 2. So this will be 74%, na? Khalid? Calculated again, this will be 74%. Yes, others, please start writing. Write till 74%. Done, all of you? All of you are done, yes or no?
Sir.
Okay, fine. Now let me share one more screen with you guys. Yes, can you see this? Face-centered cubic.
Yes, sir.
Okay. Now you can see that there are corner atoms and there are face-centered atoms, right? So those who are having, wait a second, let me stop sharing this screen, then again share it so that I will get an annotation. Okay, I am not getting any annotation tool. Why does this happen? Here. So we have, so when you see this face-centered one, okay, so focus on this face-centered atom, red atom. So it is touching 4 atoms on this layer, right? Can you see it is touching 4 atoms?
Yes, sir.
Okay, then it is also touching the back 4 atoms, the 2 blue and the 2 red, correct? Yes or no?
Yes.
Right. Now it is touching how many till now? It is touching 8 atoms. Now you have to see that this is the face center atom. It will be shared in how many rooms? In how many unit cell? Face centered is shared in how many rooms? In how many rooms? Face centered is shared in 2 rooms now. Guys, you have to remember these parts, okay? In 2 rooms. Now this face-centered atom is touching the atoms of this one room that you can see, and there is also another room which will be just adjacent to this room. It will be sharing and it will be touching the atoms of that layer also, of that room also. You can see that if I show you like this. Now let me expand it a bit. So you can see all those atoms here, right? Now, here you can see one unit cell. This is one unit cell, and you can see half atom of face centered is there. 1/8 portion of the corner atoms are there. And you can also see here, you can also see that this blue atom is touching the 4 corner ones, the 4 face centered one, and it will be also the half portion of blue atom is here. The half portion of blue atom is here. This blue atom, and then there is this, the blue atom. It is present here. Okay. So you can see that it is touching another 4 atoms from here. So in total, it is touching 4 in the same layer, then 4 in the front layer, 4 in the back layer, and then 4 3s are 12. So the face centered atom also are touching 12 atoms. So the coordination number of both the things, face center and the corner, is 12. Okay. Minashi, how are you?
Yes, sir, fine.
Okay. What was the time given to you?
4 to 5:30.
4 to 5:30. Okay, fine. So guys, since you have written all of this is 74%. Next we will be learning about the AB type packing. Okay, we'll be learning about the AB type packing. Now in this ABC type, please write voids also. Voids. Okay, there are a few students who are joining. Okay, Khalil is here, Minashi. Okay, fine. Okay, Khalil and Minashi, from next class now join 10 minutes late. Okay,
Yes.
like you have been given 4 now, then you join at 4:10. Okay, Khalil and Minashi. Okay, fine. So voids, we have tetrahedral voids and octahedral voids. So number of tetrahedral void will be equal to 2n. Okay, here n is number of atom. So as we know, the number of atom in a unit cell is equal to how much? It is equal to 4 in this case, right? Hence the number of tetrahedral void will be equal to 2 into 4, which will be equal to 8. And number of octahedral void, it is equal to n. And also n is the number of atom, and hence the number of octahedral void is equal to 4 only. It is equal to 4. So we have 8 tetrahedral voids in ABC type, and we have 4 octahedral voids. We have 4 octahedral voids. So these are the things that you had to know: the coordination number, the Z, the relation between A and R, the packing efficiency, and the number of voids So please write this number of voids, and in the next class we will be learning about the AB type packing in 3D. Khalil, can you hear me? Hello.
Yes, sir.
Okay. What time is iftar for you?
6:30.
6:30.
Yes, sir.
What is the time now?
5.
Oh, okay. So you have exact 1.5 hours. Okay. So other students, please write the information about the voids, and then